Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. States of matter. Any matter can exist in one of three states: solid, liquid, or gas. The particles that make up matter can be atoms, molecules, ions, or electrons. Solids. Here is called particle, atom, or molecule. The intermolecular forces between particles in a solid are very strong. This causes the particles to be very close together and arranged in a regular pattern. The particles in a solid can only vibrate about fixed positions. Solids have a definite shape and a definite volume, because its particles cannot move freely and are not easily compressible. Liquids. The intermolecular forces between the particles in a liquid are slightly weaker than those in a solid. This causes the particles to be close together, but not arranged in a regular pattern. The particles in a liquid can move and slide past each other. Liquids have no definite shape, but do have a definite volume, because its particles can flow to take the shape of their container, but they are not easily compressible. Gases. The intermolecular forces between the particles in a gas are very weak. This causes the particles in a gas to be far apart. The particles in a gas can move around randomly at high speeds. Gases have no definite shape and no fixed volume, because its particles can move freely to take the shape of their container and are highly compressible. Internal energy of matter. This section is the extra knowledge. Internal energy is the sum of random kinetic energies and potential energies of molecules. Kinetic energy of molecules in matter depends on its temperature. This means that kinetic energies of molecules increase as temperature increase. Therefore, kinetic energy of gases are greater than liquids, and kinetic energy of liquids are greater than solids. Potential energy of molecules in matter depends on the space between molecules. This means that potential energy of molecules increase as the separation between molecules increase. Therefore, potential energy of gases are more than liquids, and potential energy of liquids are more than solids. Change in states of matter. When a solid is changed into a liquid, this process is called melting. Liquid is changed into gas. This process is called boiling or evaporating. Gas is changed into liquid. This process is called condensation. Liquid is changed into solid. This process is called freezing. Melting processes. The solid at the melting point absorbs thermal energy to break the intermolecular forces and separate the molecules, so the potential energy increases. While the temperature is constant at melting point, so kinetic energy of molecules remain constant. Therefore, the internal energy increases when solid is changed into liquid. Boiling processes. The liquid at the boiling point absorbs the thermal energy to break the intermolecular forces and separate the molecules, so the potential energy increases. While the temperature is constant at boiling point, so kinetic energy of molecules remain constant. Therefore, the internal energy increases when liquid is changed into gas. Freezing processes. The liquid at melting point removes the thermal energy to create the intermolecular forces and reduce the separation between molecules, so the potential energy decrease. While the temperature is constant at freezing, so kinetic energy of molecules remain constant. Therefore, the internal energy decrease when liquid is changed into solid. Condensing processes. The gas at boiling point removes the thermal energy to create the intermolecular forces and reduce the separation between molecules, so the potential energy decrease. While the temperature is constant at condensing, so kinetic energy of molecules remain constant. Therefore, the internal energy decrease when gas is changed into liquid. Cooling and heating of matter. Cooling processes. Cooling occurs when the temperature of matters decrease, causing the thermal energy, is removed from matters. This causes kinetic energy of molecules decrease. While potential energy of molecules remain constant, or a bit decreasing due to compression, because the separation between molecules also remain constant, or a bit decreasing due to compression. Therefore, the internal energy of matters decrease. When the water at initial temperature of 80 Celsius is cooling until equilibrium to the room temperature of 25 Celsius, the resulting show as the graph of temperature in Celsius against time in seconds. The rate of decrease in temperature at the initial is greatest because the high different temperature between the water and surrounding, so more thermal energy loss to surrounding. The rate of decrease in temperature at the final is lowest because the small different temperature between the water and surrounding, so small thermal energy loss to surrounding. Heating processes. Heating occurs when the temperature of matters increase, causing the thermal energy is added to the matters. This causes kinetic energy of matters increase. While potential energy of molecules remain constant, or a bit increasing due to expansion, because the separation between molecules also remain constant, or a bit increasing due to expansion. Therefore, the internal energy of matters increase. When the water at initial temperature of 25 Celsius is heated until temperature of 80 Celsius, the resulting show as the graph of temperature in Celsius against time in seconds. The rate of increase in temperature at the initial is greatest because the small different temperature between the water and surrounding, so less thermal energy loss to surrounding. The rate of decrease in temperature at the final is lowest because the more different temperature between the water and surrounding, so more thermal energy loss to surrounding. Brownian motion. Brownian motion is the random motion of small particles suspended in a liquid or gas. It was first observed by the Scottish scientist Robert Brown in 1827, and it is named after him. He described the random motion of pollen grains in water, which he saw under a microscope. This observation was significant because it provides the first direct evidence that matter are made of tiny particles that are in constant motion, which is known the kinetic theory of matter. For example, when small particles, such as smoke or pollen, are suspended in a liquid or gas, they can be observed through a microscope moving around in a random manner, as shown on the diagram. This is glass cell that fills with smoke. This is a light source that shine the light through the glass cell. This lens is used to magnify. We can see the smoke particles through eyepiece of the microscope. The smoke particles are seen constantly moving and changing direction. The path of particles are random in zigzag patterns. The smoke particle is much larger than the air particles, which implies that we can see the smoke particles and cannot see the air particles by naked eyes. Air particles are moving fast and randomly around the large smoke particle. The air particles collide the smoke particle in all direction, causing the smoke particle to travel randomly with constant moving in the zigzag paths. Brownian motion is a direct observation of the random motion of individual atoms and molecules. It is a fundamental concept in physics and chemistry, and it has many applications in biology and medicine. Absolute scale of temperature. The absolute temperature, or Kelvin temperature, is Kelvin scale. Absolute zero is 0 Kelvin. This is equal to minus 273 Celsius. An increase of 1 Kelvin is the same change as an increase of 1 Celsius. It is not possible to have a temperature lower than 0 Kelvin. This means a temperature in Kelvin will never have a negative value. The Kelvin temperature of a gas is proportional to the average kinetic energy of its molecules. This means that the average kinetic energy of gas molecules increases as the temperature increases. The convert between temperatures in the Celsius scale and the Kelvin scale, use the equation T in Kelvin equals theta in Celsius plus 273. At absolute zero is lowest temperature that particles have no kinetic energy. Pressure of gases. Pressure of gas is produced by the collisions of gas molecules on the surface of an object. When gas molecules collide with the surface, they bounce off, causing changes in the momentum of the gas molecules due to changes in their velocity directions. These collisions result in forces being exerted on the surface of the object, as force is the rate of change in the momentum. Therefore, there is pressure due to the gas, as pressure is defined as the force per unit area. The relationship of pressure and volume of gases when fixed mass and temperature. This is called the Bowley's law. If the temperature and mass of a gas remain constant, the pressure of gas decreases when it is compressed. This is because the volume of the container decreases, and the gas molecules are closer together. This causes the gas molecules to collide with the wall of the container more often. Therefore, the total force per unit area increases and pressure also increases. If the temperature and mass of a gas remain constant, the pressure of gas increases when it is expanded. This is because the volume of the container increases, and the gas molecules are further apart. This causes the gas molecules to collide with the wall of the container less frequently. Therefore, the total force per unit area decreases and pressure also decreases. From this information, we can see that the pressure is inversely proportional to the volume of a gas. The graph of pressure in Pascal against volume in cubic meters, as shown in the diagram. It is the reciprocal graph. We can write the reciprocal equation of the graph as P equals constant value divided by V. This means that the product of the pressure and volume of gas is constant. Therefore, P1 equals constant value. P2 equals constant value. We can write the equation as follows. P1 V1 equals P2 V2, where P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, V2 is the final volume. The relationship between pressure and temperature of a gas, when fixed volume and mass of the gas. If the volume and mass of a gas remain constant, the pressure of gas decreases. When temperature is decreased. This is because the speed of the molecules decreases as temperature decreases. This causes the gas molecules to collide with the wall of the container less often and less force. Therefore, the total force per unit area decreases and pressure also decreases. If the volume and mass of a gas remain constant, the pressure of gas increases. When temperature is increased. This is because the speed of the molecules increase as temperature increases. This causes the gas molecules to collide with the wall of the container more often and harder. Therefore, the total force per unit area increases and pressure also increases. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. When a solid, liquid or gas is heated, its particles gain kinetic energy. This causes the particles of solid to vibrate faster, or the particles of a liquid or gas to move faster. The increased kinetic energy of the particles causes the distance between them to increases, and the volume of substance to increase as well. This is called expansion. When a solid, liquid or gas is cooled, its particles lose kinetic energy. This causes the particles of solid to vibrate more slowly, or the particles of liquid or gas move more slowly. The decreased kinetic energy of the particles causes the distance between them to decreases, and the volume of substance to decrease as well. This is called contraction. Solids have very strong intermolecular forces between particles, which causes them to be tightly packed together. This makes it difficult for solids to expand and compress. Liquids have strong intermolecular forces between particles, but they are not as strong as the forces in solids. This allows liquids to expand and compress more easily than solids. Gases have very weak intermolecular forces between particles, which causes them to be far apart each other. This makes it easy for gases to expand and compress. Therefore, solids are the least expansion and compression, but gases are the most expansion and compression. The everyday application of thermal expansion. Bimetallic strip. A bimetallic strip is made of two different metals that expand at different rates when heated. This causes the strip to bend when the temperature changes. Bimetallic strips are used in many temperature-activated switches, such as those that turn on a fan when the room gets too hot. Railway lines. Railway lines are laid with expansion gaps to allow for thermal expansion. This prevents the tracks from buckling when they get hot in the summer. Thermometers. Thermometers use the expansion of a liquid to measure temperature. The most common liquid used in thermometers is mercury, but alcohol is also used. When the thermometer is heated, the liquid expands and rises up the tube. The height of the liquid in the tube is then used to measure the temperature. Electrical cables. Electrical cables must have some slack in them to allow for thermal expansion. This prevents the cables from breaking when they get cold and contract. Car tires. The air in car tires expands when it is heated. This is why car tires are inflated to a higher pressure in the summer than in the winter. Jar lids. If you have ever tried to unscrew a stuck lid off a glass jar, you know that it can be difficult. But if you run hot water over the lid, it will expand slightly and become easier to unscrew. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. When an object is heated, its temperature increases. This causes the average kinetic energies of all particles in the object to increase. The potential energy of particles may remain constant, or increase slightly due to expansion, because the separation between particles may also remain constant, or increase slightly due to expansion. Therefore, the internal energy of the object increases. This internal energy is also known as the thermal or heat energy. The thermal energy, delta E, added to an object of mass, m, to increase its temperature, delta T, can be written as the equation delta E equals m c delta T, where delta E is the thermal energy in joules, m is the mass in grams or kilograms, c is the specific heat capacity of the substance in joules per gram degree Celsius, or joules per kilogram degree Celsius. Delta T is the change in temperature in degrees Celsius or kelvins. Specific heat capacity, C, is defined as the thermal energy that required per unit mass to increase the temperature by 1 degree Celsius or Kelvin. It remains constant for a given substance. The experiment to measure the specific heat capacity of a metal block. We set up the apparatus as shown in the diagram. The thermometer is used to measure the change in temperature. The heater is used to supply heat to the metal block. It is connected to a voltmeter and an ammeter to measure the power input. The metal block is insulated with an insulating material such as rubber, plastic, or cloth to reduce thermal energy loss to the surroundings. The stopwatch is used to measure the time it takes for the temperature to change. The procedure of measuring the specific heat capacity is as follows. First, measure the mass of the metal block using a scale balance. Second, turn on the heater and wait for it to reach the maximum heat. Then, start the stopwatch and record the initial temperature, T1. Third, read the voltage, V, on the voltmeter and the current, I, on the ammeter. Fourth, time the interval for T seconds, then record the final temperature, T2. Fifth, calculate the thermal energy added to the metal using the equation, delta E equals P multiplied by T, where P is the power input, which P equals voltage, V, times current, or I. Therefore, C equals delta E over M delta T. And substitute delta E to V, I, T. Delta T equals T2 minus T1. Specific heat capacity, C, calculated from this experiment will be more than the actual value of the metal block, because some of the thermal energy is lost to surroundings, causing a smaller change in temperature. The experiment to measure the specific heat capacity of a liquid. We set up the apparatus, as shown in the diagram. The apparatus are changed at the insulated container that fills with a liquid. There is an insulated lid to reduce thermal energy loss to the surroundings. The procedure of measuring the specific heat capacity of a liquid is the same as for a solid, with the following changes. The mass of the liquid is measured by weighing the empty insulated container, and then weighing the container with the liquid. The difference in mass is the mass of the liquid. The specific heat capacity is calculated using the equation C equals delta E over M delta T, where delta E is the thermal energy added to the liquid. M is the mass of the liquid. Delta T is the change in temperature. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Here is the graph that shows the relationship of change in temperature in degrees Celsius and time in second of the water at sea level of atmospheric pressure. Between -10 and 0 Celsius, the water is a solid state as ice. It is heated. At 0 Celsius, the ice melts and becomes liquid. There are the solid to mix with liquid in this section. At melting, the temperature is constant, because the ice absorbs latent heat to break the intermolecular forces and separate molecules, causing the potential energy increase, while kinetic energy of molecules remains constant. The latent heat is the energy required to change the state of a substance. Between 0 and 100 Celsius, the water is a liquid state. It is heated. At 100 Celsius, the water boils and change becomes from vapor. There are the liquid to mix with gas in this section. At boiling, the temperature is constant, because the water absorbs latent heat to break the intermolecular forces and separate molecules, causing the potential energy increase, while kinetic energy of molecules remains constant. Between 100 and 120 Celsius, the water is a gas or vapor. It is heated. Specific heat capacity of water is more than ice, and the specific heat capacity of ice is more than vapor. This means that it takes more energy to raise the temperature of water by 1 degree Celsius than it does to raise the temperature of ice or vapor by 1 degree Celsius. This causes the graph between 0 and 100 Celsius is least steep, and the graph between 100 and 120 Celsius is most steep. In reverse process, when a vapor at 100 Celsius removes the thermal energy and change states from gas into liquid, which is called condensation. At condensation, the temperature is constant, because the gas removes latent heat to create the intermolecular forces, causing the potential energy decrease, while kinetic energy of molecules remains constant. When a water at 0 Celsius removes the thermal energy and change states from liquid to solid, this is called solidification or freezing. At solidification, the temperature is constant because the water removes latent heat to create the intermolecular forces, causing the potential energy decrease, while kinetic energy of molecules remains constant. Boiling and evaporation. Boiling occurs when a liquid reaches its boiling point and continues to absorb energy to break the intermolecular forces and separate molecules. This causes the potential energy of the molecules increase, while their average kinetic energy remains constant and temperature also remains constant. Evaporation occurs when the most energetic molecules at the surface of a liquid break the intermolecular forces and escape from the liquid surface into the air. This leaves the lower energies molecules behind, which causes the temperature of the liquid to decrease. The similarity between boiling and evaporation is the both processes to change states from liquid into gas. The difference between boiling and evaporation. Boiling occurs only at the boiling point of a liquid, while evaporation occurs at any temperature between melting and boiling points. Boiling occurs throughout the liquid, producing bubbles, while evaporation occurs at the surface of the liquid. Temperature remains constant during boiling, while temperature decreases during evaporation. Factors that affect the rate of evaporation. Temperature. The higher the temperature, the faster the rate of evaporation. This is because there are more the most energetic molecules at the surface that can escape into the air. Surface area of liquid. The larger the surface area of the liquid, the faster the rate of evaporation. This is because there are more the most energetic molecules at the surface that can escape into the air. Wind speed. The faster the wind speed blows over the surface of liquid, the faster the rate of evaporation. This is because the wind removes the water vapor from the surface of liquid, allowing more water vapor escape. Humidity. The lower humidity, the faster the rate of evaporation. This is because there are less water vapor in air, allowing more water vapor escape. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Thermal energy transfer. If there is a difference in temperature between two objects, causing thermal energy transfer from the hotter object to the colder one, this will continue until both objects are at the same temperature. We say that they are in thermal equilibrium. Thermal energy can be transferred from the hot object to colder object by conduction, convection, and radiation. Conduction. Conduction occurs mainly in solids. Particles in liquids and gases are much more free to move around than in solids, which is why they usually transfer energy by convection instead of conduction. At the hot end of the solid bar, the atoms of particles gain kinetic energy and vibrate faster. The atoms in a solid are close together, and so they collide with neighboring atoms, which in turn start to vibrate faster. In this way, heat energy is transferred from the hot end to the cold end of the solid bar. If a solid bar is the metals, which have free-moving electrons, this causes thermal energy transfer by conduction faster. This is because free electrons gain kinetic energy at the hot end of the bar. These free electrons pass on their kinetic energy through collisions with other electrons and metal atoms as they randomly diffuse through the metal. In this way, thermal energy is conducted from the hot end of the bar to the cold end. Good conductors are the substance that can transfer heat energy easily because they have free-moving electrons. Good conductors are mainly the metal, such as silver, copper, iron, aluminum, brass, and others. Poor conductors are called insulators, which are the substance that transfers heat energy difficultly, because they have no free-moving electrons. Insulators are mainly non-metal, except for graphite, which is a conductor. An experiment to distinguish between good and bad thermal conductors. Metals are better conductors of heat than non-metals. However, some metals are much better conductors than others. In this investigation, the thermal conductivity of 4 metals is compared, and the metals can then be placed in order from the best conductor of heat to the poorest. Set up the apparatus as shown in the diagram. For metals, rods are used to be iron, copper, brass, and aluminum. Attach a drawing pin to the end of each rod with a small blob of Vaseline. The ends of the rods, without the drawing pins, should be brought together so that they can be heated equally. Heat the ends of the rods equally with a blue Bunsen flame. Record the time taken for each rod to lose its drawing pin. When the temperatures of the far ends reach the melting point of wax, the pins drop off. The pin on copper falls first, showing it is the best conductor, followed by aluminum, brass, and then iron. An experiment to show that water is a poor conductor of heat. Set up the apparatus as shown in the diagram. Ice is trapped at the bottom of the boiling tube with a piece of metal gauze. When the water at the top of the boiling tube is heated strongly, it boils. The ice at the bottom of the tube does not melt. This shows that water is a poor conductor of heat. However, if the ice is allowed to float normally, it melts quickly when the water is heated at the bottom of the test tube. This is because the water molecules can move, so the water heats by convection. Water, like other liquids and non-metal solids, is a poor conductor of heat energy, because its molecules do not have free-moving electrons to easily pass on their kinetic energy to their neighbors. So the heat can only be transmitted through the vibration of the particles. Gases are very poor conductors of heat energy, because their molecules are very far apart, so kinetic energy cannot be transmitted from one molecule to another. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Convection. Convection is the transfer of heat energy by the movement of currents within a fluid, which are liquids and gases, where the particles are free to move around. This is because the density of the fluid changes when it is heated. An experiment to demonstrate convection in water. A few crystals of potassium permanganate are placed at the bottom of a beaker of water. They dissolve and color the water near them purple. When the water is heated, the purple water rises above the Bunsen flame, moves across and then falls at the other side of the beaker before returning to the flame to be heated again. This movement of water is called a convection current. The reason why warm water rises. This is because the water is heated, its molecules gain kinetic energy and move around faster. They move further apart, and so the density of the water decreases. The warm, less dense, water rises. As the water begins to cool, warm water rises and pushes the cooler water over. The cooler water sinks. This is because the molecules of cooler water have less kinetic energy. They move closer together, and so the density of the water increases. The cooler, more dense, water sinks. When the warm water rises, then cooler, denser water moves across to take its place. This process continues until the water is heated evenly throughout. An experiment to demonstrate convection in air. Set up the apparatus as shown in the diagram. Place a lighted candle below one of the glass tubes. Hold a smoking paper above the other glass tube. The air above the candle flame gets hot and rises. Cooler air is then drawn from the other tube to replace the hot air. Smoke is used so that we can see how the air moves. The movement of hot and cold air set up convection current. The hot air rises. This is because the air above the candle is heated, its molecules gain kinetic energy and expands. The expanded air is less dense than the surrounding air and rise out of chimney. The cooler air sinks. This is because the molecules of cooler air have less kinetic energy, and so they are closer together. This causes the density of cooler air to be more than the hot air. Since the cooler air is denser, it sinks into chimney. Material that have trapped air in them, such as cotton wool or bubble warp, are good indicators, because air does not conduct heat, and trapped air cannot convection heat either. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Radiation. Radiation is the transfer of thermal energy from one place to another by means of electromagnetic waves. Radiation can occur in a vacuum, particles of matter are not involved. Radiation is emitted by all bodies above absolute zero and consists mostly of infrared radiation. As an object gets hotter, it will also emit more thermal radiation. Thermal equilibrium. As an object absorbs thermal radiation, it will become hotter. If the rate at which an object emits energy is less than the rate at which it absorbs energy, then the object will heat up. If the rate at which an object absorbs energy is less than the rate at which it emits energy, then the object will cool down. Both processes will always move towards thermal equilibrium. Eventually, the object will reach a point of constant temperature where the rate at which it absorbs radiation is equal to the rate at which it emits radiation. At this point, the object will be in thermal equilibrium. Emitters and absorbers of thermal radiation. Matte or dull black surfaces of the objects are good emitters and good absorbers of thermal radiation. Shiny white or silver surfaces of the objects are good reflectors, but worst absorbers of thermal radiation. There are two factors which affect the rate at which energy is radiated from the surface of a hot object. The temperature of the surface. A hotter surface radiates energy at a greater rate. The surface area, energy is radiated at a greater rate from a bigger surface area. An experiment to distinguish between good and bad emitters of infrared radiation. Set up the experiment as shown. The metal cube has its vertical sides painted with 4 different surfaces: matte black, white, shiny black, and silver. Fills the cube with boiling water. Leave for 1 minute to enable the surfaces to heat up to the temperature of the water. Use the infrared detector to measure the intensity of infrared temperature from each surface, or the temperature of the surface. Make sure that the detector is the same distance from each surface for each reading to ensure that this is a fair test. The results show that the highest temperature at the matte surface and lowest temperature at the silver surface. Therefore, matte surfaces are the best emitters of the thermal radiation. Silver surfaces are the worst emitters of thermal radiation. Another experiment to investigate the emitters of thermal radiation. Set up the experiment as shown. One can has a matte black surface, and the other can has a white surface. Fill the 2 cans with hot water. Use thermometer to measure the temperatures. Record and compare the results. Make sure that the initial temperatures of water in both cans are the same. Same time interval is used to record the temperatures. This ensures for a fair test. Matte black can has higher drop in temperature than white can at the same interval. This shows that the matte black surface is good emitter. An experiment to distinguish between good and bad absorbers of infrared radiation. Set up the experiment as shown. 2 metal surfaces are painted with matte black and white. They placed at a same distance from the heater to ensure that this a fair test. Two similar thermometers are attached at the back of two surfaces. The initial readings are taken on the two thermometers. The radiant heater is switched on and the temperature on the two thermometers recorded after 1 minute. The temperature at matte black surface is higher than at white surface after 1 minute. Therefore, the matte black surfaces are the best absorbers of thermal radiation. White surfaces are the worst absorbers of heat radiation. Another experiment to investigate the emitters of thermal radiation. Set up the experiment as shown. One can has a matte black surface, and the other can has a white surface. Place them at a same distance from the heater to ensure that this is a fair test. Fill the two cans with cold water at the same initial temperature to ensure that this is a fair test. Use thermometer to measure the temperatures at same time interval to ensure that it is a fair test. Record and compare the results. Greenhouse effect. If the Earth had no atmosphere, the temperature on the surface would drop to about -180 at night, the same as the Moon's surface at night. This would happen because the surface would be emitting all the radiation from the Sun into space. Therefore, the atmosphere of the Earth causes the Earth's temperature. The radiation from the Sun enters the Earth's atmosphere to reach the Earth's surface. Radiation is absorbed by the Earth's surface and re-emitted at longer wavelengths, such as infrared radiation. This is because the Earth's surface temperature is smaller than the Sun's surface temperature. Some emitted thermal radiation passes through the atmosphere into space. Some emitted thermal radiation is absorbed and reflected back by air in the atmosphere, such as water vapor, methane and carbon dioxide, which prevents it from escaping into space. These processes makes the Earth warmer than it would be if these gases were not in its atmosphere. The temperature of the Earth is affected by factors controlling the balance between incoming radiation and radiation emitted from the Earth's surface, such as the rate of radiation from Sun reflected back into space, the rate of radiation absorbed by the Earth's atmosphere or by the Earth's surface, the rate of radiation emitted from the Earth's surface and from the Earth's atmosphere into space. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Heating the room by convection using the heater. When a heater is turned on, the air around it is heated. This causes the air to become less dense than the surrounding air, and warm air rises. As the air begins to cool, warm air rises and pushes the cool air over. Warm air displaces cooler air. So, the cooler air, denser, and air sinks. Cool air flows across to take the place by the rising of the heated air. This process continues until the warm air is heated evenly throughout the room. The same process happens when a room is cooled by an air conditioner. The air conditioner cools the air, making it denser than the surrounding warmer air. The cooler air sinks. Cool air displaces warmer air. The warmer, denser, air rises. Warm air flows to take the place by the sinking, cooled air. This process continues until the room is cooled evenly. Sea breezes. During the day, the sun's infrared radiation heats the land more than the sea. This causes the air above the land to become warmer and less dense than the air above the sea. The warm air above the land rises, creating a low-pressure area. Cooler air from above the sea, more dense, and sinks, creating a high-pressure area. Cooler air above the sea then flows in to fill the low-pressure area. This convection current causes a sea breeze to blow from the sea to the land. Land breezes. Land breezes is the reverse process with sea breezes. During the night, the land cools off more quickly than the sea. This causes the air above the land to become cooler and denser than the air above the sea. The cooler air above the land sink, creating a high-pressure area. Warmer air from above the sea, less dense, and rises to create a low-pressure area. The cooler air from above the land then flows in to fill the low-pressure area. This convection current causes a land breeze to blow from the land to the sea. The condition, convection and radiation of a fire burning wood. The woods are burned by a fire, as shown. Heat energy is transferred through a solid to the hand by conduction. Heat energy is transferred through air to hands at the side of a fire by radiation. Heat energy is transferred through air to the hands above a fire by convection, because warm air above a fire rises. This is because warm air is less dense than the surrounding air. Vacuum flask. The stopper is made of an insulator, such as plastic, rubber, or other materials, which reduces heat energy loss by conduction. The stopper also stops heat loss by convection and evaporation. The gap contains no air. So, there are no particles to pass on the heat energy by conduction or convection. The silvered surfaces reflect infrared radiation and reduce heat energy loss by radiation. Kitchen pan. The kitchen pan is heated using a fire as shown. Kitchen pan is made of the metal, such as brass, aluminum or others. Thermal energy from a fire is transferred to the metal pan by radiation. Thermal energy is then transferred through the metal pan by conduction. Thermal energy is transferred from the metal pan to the water by conduction. Thermal energy is transferred through the water by convection, because hot water above the bottom pan rises. This is because hot water is less dense than the cooler water above it. Therefore, cooler water sinks and moves down to take its place. The plastic's handle is an insulator to reduce thermal energy transfer to hand by conduction. Radiator in a car. A radiator is a heat exchanger in a car that helps to keep the engine cool. The coolant liquid flows through the tubes inside the combustion engine. The coolant liquid absorbs the engine's heat by conduction and then gets heated itself. The heated fluid rises by convection and then travels through a rubber hose to the radiator in the front of the car. As it flows through the thin tubes in the radiator, the hot liquid is cooled by conduction using the airstream entering the engine compartment from the grille in front of the car. Once the fluid is cooled, it returns to the engine to absorb more heat. The air picks up heat from the coolant by convection. Heated air is blown away by the fan, and colder air replaces it. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.